we're going to store 123. And these instructions, the two instructions at the bottom, they take our register value and take it to the memory location that register RDI or register RSI are pointing to. So this is how we use the addressing modes, where we specify to use the register as an address. So the more elaborate addressing mode that we briefly talked about in the previous lecture is the displacement mode, where we have the parentheses and a register R, and then we have the displacement right here. D is displacement. So what it means is you take the contents of the register R, you add the displacement, and you go to the memory location register R plus D. All right. So here's an example at the bottom where you have RBP register. It has some value in it, which is a memory address. And what we are saying, add 8 and bring the value stored at the memory location RBP plus 8 into register RDX. When might this be useful? What is going on here?
The online people can't see the slide.
Well, I don't know how I can handle online chat and in person at the same time. I don't know. Well, can you see it now? Can you see the slides now? All right, everything is good. Sorry, let me provide better support for online students starting the next lecture. I'll take the feedback and I'll bring someone who can handle the online chat, and I kind of feel. Okay, so one question I have is, when do you think, you've been writing C programs, you've been writing other programs, when can this displacement help? Indexing arrays, indexing structures. When you have a base address of a structure, of a data structure, of an array, and you want to reach a specific field or a specific location within the data structure. In fact, there is a very x86 provides a very powerful addressing mode where you can specify the base register, the base address, the index, and a scaling factor. So what happens in the end is you add the contents of the base register, you multiply the scaling factor with the index register, and you add the displacement, and you go to that memory location. Now, let's see a very quick example. And then there are special cases where you omit some things in certain cases. So here's an example. So what's this scaling factor? So let's say I have an array. Seven and 8. And this is the base address, and this is an array of integers. An integer is 4 bytes. So the byte addresses are 0, 4, 8, 12, 16, right? So say I have a base address, and I have this array is called array, and I want to access array I. How can I do that? So suppose that the base address is in register RBX, and the index I is in RDI. And I want to get array I, the byte address. So what is the formula? What is the general formula for from the base? I want to go where? In terms of bytes. I multiplied by 4. This 4 is the scaling factor. So Intel provides 1, 2, 4, 8 as the scaling factors. Why?
To allow for different size data types.
But why stop at 8? The typical data types, the native data types are one byte. What is 1 byte? Char, character. Word is 16 bits. Long is, int is 4 bytes, and a long is 8 bytes. So these are the typical data types that we encounter. And there is support for that at the ISA level. So C to x86, this is why we say that C is very close to the actual hardware. If you look at a C, if you look at array I, there is one instruction we will soon see that can do the address computation. And this is the addressing mode that Intel provides to access different array elements or different fields of a data structure. You can combine different types into a single object in C, even though C is not really an object-oriented language. How do we do that? There is something called a struct or a structure, which we can use to combine different types into a single object. Okay. So you don't always have to use the displacement, the base register, the index register, the scaling factor. Depending on your specific situation, you can omit some of those things. If you have 2-dimensional arrays, you need everything. If you have 1-dimensional array, you need only probably just a base index and a scaling factor. And you will encounter different examples in the labs when we go to C2x86. Some examples of address computation. Right, so at the very bottom, you see you are adding the displacement. There is no base register, and you're just multiplying the scaling factor 2 by RDX. Okay, I want to talk about a very interesting and powerful instruction, leak. Leak, the first part stands for load effective address. This instruction looks like a data movement instruction, looks like a move instruction, except it doesn't do any movement at all. It is just to compute the pointers or the memory addresses of a memory reference instruction that comes later in the program. It is there to facilitate the calculation of memory addresses. So whenever we have something like this, we are saying X is an array, I is my index, Xi is a value. But when you put an ampersand in C, it becomes an address. So what I'm saying is address of element I inside the array X. Whenever you have to compute such addresses, you use the leak instruction. And then at a later point, you use a move instruction to actually do the movement. So leak can also be used for doing ordinary computations, where you're not calculating a memory address, but you are just doing a arithmetic operation. So here, the function m12 says return x multiplied by 12, assuming that x is passed to the function in register. Which register is that? RDI. What we are doing here is, first we are saying RDI plus RDI multiplied by 2. All right? The same addressing mode that we just looked at on the previous slides with the move instruction. Inside the parentheses, we are saying 2 is the scaling factor, RDI is the base, and RDI is the index register. What we get as a result of this instruction in array X is X plus X multiplied by 2, which is 3X. Now, the program, the function here says X multiplied by 12. So what is the bottom instruction doing? Even though you haven't looked at that instruction, can you guess? Whenever we do a shift arithmetic left, whenever we shift left 1 bit, we are actually doing a multiplication by 2. This is how binary numbers work. You already know that. So the compiler can look at the function and realize, oh, I can use leak to do this very efficiently. And there is no memory transfer, there is no address generation or address computation, but the compiler is smart enough to use the leak instruction to do this arithmetic operation. Now, all right, here is something interesting. Now, structs is something that you're going to look at in the next lab, but I can give you some intuition. In C, you can create objects by combining them together into a single type. This struct consists of homogeneous types, 2 integers, but instead of integer, you can have a float, a double, a character array, and this is how you create objects in C. All right, so then I can say P is a pointer to an array points. So assuming that points is an array of point data type, this points I dot y coordinate, and the ampersand is the address. So in memory, points looks like x, y, x, y, x, y. It is like, I'm omitting the quad thing to save space. I have a bunch of points in memory stored contiguously. It is like an ordinary array, but it is not an array of integers or longs. It is an array of points, and point is a new type, a new structure that I have created that takes two integers and pack them together into a single type. This is how you create new types in C, new structures. Now, I have this array, and what this, it's a silly statement. Don't write programs like that. But this statement says, go inside the points array, go to index I, take the y coordinate, and give me the address. So I want you to focus on this instruction below. You know, you can do all of this in one instruction. That's the power of Leak. And that's why we say that C to x86, C to assembly is a very one-to-one correspondence. It's not, if you go to Java, other languages, there are a lot more instructions to do the same thing. All right, so here we are computing this memory address. That statement up there, pointer P equals, go inside the points array, go to index I inside the points array, go to the y coordinate, give me the address. Happens in one instruction. RDI is the base address of the points array. What do you think is in RBX? What? What is in RBX? Index, right? Index. RDI, sorry. What is in RBX? Index, right? So RDI is the base address of the array. RBX is the index. Why am I multiplying by 8? Why is the scaling factor 8? Because the size of the structure is 8 bytes. I have created a new data type in C whose size is 8 bytes. Now, when I do the scaling of the index by 8, I go to points I, right? At this point, I'm at points I. Where do I really want to go? Where is y coordinate? +4, which is right here, the power of Leak. It can give you very complex addresses, very complex address calculation in C can be done with one instruction. Now, one important thing is that the processor, the CPU internally can do this whole thing in one cycle, or it may break it down into many small operations. And Intel processors do that because this is a very complex instruction. This is very difficult to implement, to do that in one clock cycle. Sometimes they break it down into many small micro operations, but we don't have to worry about that here. We get this one instruction that the compiler can translate that address computation. Well, like I was saying, the purpose of all this is not to, you won't be writing assembly programs. We will just have you read some assembly, disassemble object code, binaries, and try to guess what is happening. So here are some arithmetic instructions. I really wanted to cover the memory transfer, the data movement instruction, and addressing modes in detail. These are all the arithmetic instructions, and they make intuitive sense at this point. AND, OR, XOR, add, subtract. There are also increment, decrement, negate, not instructions. We can look at an example of how the compiler does the transformation of arithmetic code in C to assembly. Oh my God. How do we use this? Jesus. This is a. All right, so I have this code on the left-hand side. All right, let's do it quickly. And my variables are stored in these registers, okay? So the first statement is very simple, right? X plus Y, add RDI. So here is XY in RDI, RSI, and here I'm just adding them together. So what's happening after that? Oh, by the way, they're using leak here to do the X plus Y. So T2 is RAX plus RDX. RDX is the argument Z. So what's happening here now? So really what we care about is the result value. Everything else is temporary. Everything else is transitory. We don't really care about. Whoever calls this function needs our value. So the compiler is smart enough to know that, you don't really need T3. You don't really need to compute T3 faithfully, like one instruction after the other. So it's going directly to T4. Because you need T4 for T5, and you need T5 for RWell, and you need to return RWell, okay? So here, it's doing, what does this look like? What is in RSI? What is this producing? What is in RDX after this instruction? Think about it. 3 times RSI. What is in RSI? Y. So why is the compiler doing that? Who says do 3y, 3 multiplied by y? Who is saying, 3 that's not what the program is saying. Why is the compiler doing 3 multiplied by y? Because later on, they want to use this trick once again. Multiply 3 times y multiplied by what? 16. You get 48y. You need 48y for T4. And then the next instruction is a leak instruction that adds 4 and stores T5 in RCX. And then you do the multiplication and you get the final value. So when you look at, when you disassemble programs, binaries, object codes, you have to realize that, you have to keep in mind that the compiler might have done its own game, right? Or its own optimizations. You don't get always a one-to-one correspondence between C and so similar to ARM, every processor has condition codes that tells you something about the result of an operation. So carry flag, zero flag, sign flag, overflow flag, these are the bits in the flags register, or we call them condition codes. And the rest of the slide is just revisiting the registers that we have looked at. What you remember as program counter that contains the address of the instruction that is executing. Here we call it the instruction pointer. That's the thing, the pointer to the instruction that is executing, RIP. So these flags, these condition codes can be set, are set implicitly, which means you don't have to do anything special. You just execute an instruction and the condition codes will be set for you automatically by the processor. Most arithmetic instructions set the condition codes except leak. Leak does not set the condition codes. Or you can set the condition codes explicitly. There are special instructions that can set the condition codes for you. And we'll see the use of that. Now in ARM, which instruction was used to set the condition codes explicitly? Explicitly. CMP, compare, right? We have a similar instruction here, compare Q. Once again, we are using Q because we are looking at 64-bit ISA. So carry flag, zero flag. Compare instruction has two operands. Compare BA, and then you compute the processor, the CPU computes A minus B, and then sets the condition codes based on whether there's a carry, if the result is 0. So if A and B are equal, then the 0 flag is set. Remember overflow? So here is, not mathematically rigorous definition of overflow, but intuitively, if A is greater than 0, B is less than 0, and you do A minus B, you cannot get A minus B less than 0. If A is greater than 0, B is less than 0, there is no way in the world you can get A minus B less than 0. And this is what tells the processor there must have been an overflow. And similarly, if A is less than 0, B is greater than 0, then A minus B cannot be greater than 0. So this is the intuition behind the overflow flag. So this is the first way to explicitly set the condition codes. The second way is the test queue instruction. This is very similar, but it uses, it does A and B. This is an and then set the condition codes based on the value of source 1 and source 2. Typically, we create a mask. B is a mask, and we do an AND with A to figure out something about A. Suppose we have a number A, and we want to figure out, what is it? Is it a positive number, negative number? What are its properties? We can create a mask where the most significant bit is 1, for instance. We do an AND with A, and it tells us something about A. So if A and B equals 0, then the 0 flag is set. If A and B is less than 0, then the sign flag is set. So we can create a mask, apply it to a number, do an AND of that mask with a number that is stored in A, and then the result tells us something about A. So condition codes can be are set implicitly for most arithmetic instructions except leak. We can explicitly set condition codes using test queue and compare. The point is, how can we read the condition codes? So there are different ways of doing that. So let's look at the setx instructions. What they do is they set the lower order byte of a destination to 0 or 1 based on different combinations of condition codes. So equal, not equal, S, not S. The conditions are right here. It's very similar to the ARM way of doing it. So you can set the low order byte of a register. Let's look at an example. It will be more clear than that. Okay, how do we use the setS instructions? Okay, here's an example function. And what it's doing is returning x is greater than y. And assuming that x is in RDI, y is in RSI, how can we do this efficiently? Now look at this code here. And the text is, I explain it later. So we need to find a relationship between x and y. Is x greater than y, less than y? We are going to compare RSI and RDI. So this is a comparison operation. We are comparing x and y. And then we are using the set instruction. If x is greater than y, what will happen? We've been using the 64-bit x86, and we are used to RAX, RBX. But you can, if you want to use only the low order byte of a 64-bit register, you can do it with AL. So RAX is 64 bits, EAX is 32 bits, and then AL is the least significant byte. Okay, so based on what we know about set instructions, what do you think is this instruction doing? Set G AL. The compare instruction has set the proper condition codes after comparing x and y, after doing x minus y or y minus x. If x is greater than y, then the low order byte of register RAX will be set to 1, right? 1 will be stored in AL. So this is our 64-bit register. And because Intel, in 1978, the first 8-bit processor, then 16-bit processor, then 32-bit, then 64-bit, it has evolved. We can, and it's backward compatible, we can still access the low order byte of this register. So if we want to access the full 64 bits, we use RAX. If we want to use 1 byte only, we say AL. So after comparing X and Y, this instruction will set AL to 0 or 1. This is an interesting instruction. Now, we are writing 64-bit code, and you will be looking at 64-bit code. You know the calling conventions. You don't know the x86 conventions. We will look at that in a bit. But for now, I'm just going to tell you that functions return the result in register RAX. Okay? So I want to return something in RAX. Recall the calling conventions and everything. There needs to be a protocol. The calling function needs to put all the parameters in specific places, and the callee needs to return something in a specific register. All of that thing. Now, I have something in my low order byte of the 64-bit register in AL, but I can't return AL. I want to return an integer. This here is an integer. I have to return a 32-bit number, not a byte. And the 32-bit register is EAX. E stands for extended. When they extended it from 16-bit to 32-bit, they called AX EAX. So AL, AX, EAX, RAX. That's the evolution. And you can access all these registers because the ISA is backward compatible. This instruction here the move Z BL instruction, what it does, it's a variant of the move instruction. It takes a byte. B stands for the granularity of the source operand. B stands for what is the data type of the source operand, and B stands for byte. L stands for the data type of the destination operand. And the instruction says, move a byte into a long and 0 everything else. So we take whatever is stored in AL, we copy it into EAX, and we 0 the rest of RAX. So this instruction, move ZBL, will set up RAX for returning to whoever called this function. In RAX, you will get a 1 or a 0, and this instruction will make sure that everything else is zeroed. Now, there is an interesting property of x86-64. You know, what this instruction is really saying is move a byte into a long and zero everything else in the remaining bytes. When you move a byte to a long, how many bytes are left? How big is a long? Whenever a long is 4 bytes, whenever an x86 instruction produces a long value, it zeros the rest of the bytes in a 64-bit register. So RAX so whenever an instruction produces a 32-bit value, you zero everything else. So okay, so we have more of these instructions. We have BW, which is taking a byte and moving it to a 16-bit register. BL, 4 bytes to 32 bits. WL, BQ, and WQ. What kind of operation does it remind you of in a high-level language like C? What do we call it? When we take a smaller data type casting. So whenever the compiler sees a cast, it uses one of these instructions to do the casting. Okay. So once again, this is the source data type, and this is the destination. Source, destination. Q is quad word. B is a byte. And then there are instructions that do the sign extension instead of zeroing. Okay, I will return to this property. It will become more clear with some examples. But basically, when they move from 32-bit ISA to 64-bit, they have this convention that an instruction that produces a 32-bit value will zero the rest of the bytes in the 64-bit register. All right. So this instruction here, move long, copies EAX into EBX, it produces a 4-byte value. So it will make sure that the remaining bytes in RBX are zeroed. These are the remaining 32 bits. Okay, we'll see more examples of that. I want to talk about the jump instructions. So jump instructions use the same method. You have you can use these conditions, and you can jump based on the condition codes. So a direct jump is where there is no condition involved. So a direct jump .L2, think of it as a label. A label is like an address in memory. Typically, we jump to labels or to memory addresses, memory locations where what is stored? Instructions or code, right? We use jumps, we use direct jumps to jump to parts of memory, to a specific location in memory where, for instance, instructions or code for a specific function is stored. So we jump around. Instead of going to the next instruction, instead of incrementing the program counter by 4 or 8, we use jumps to go to a different part of the program. Indirect jumps. So here, the address of where we jump is provided as a constant in the instruction. In indirect jumps, this address is provided in a register. All right. So the address of where to jump in memory is stored in a register. Now, what is your intuition about the last jump? Where is the address stored of where to jump? So this is a syntax thing. The star, this is just a syntax thing. You need to put a star for indirect jumps. So jump RAX, go to register RAX, whatever is stored in that register, treat it as an address and jump to that address. And at that address, there is code. There are instructions that the processor will start executing instead of going to the next instruction. What is the last jump doing? Whenever you have parentheses, what happens? Treat register RAX as an address, go to that memory location, and whatever is stored at that memory location is the address of where to jump. We write complex programs, and we need support from the ISA that sometimes looks funny. We will see an example of how this is very powerful. We're going to read the register RAX. We want to treat it as a memory address. We're going to go to that memory address, and whatever is stored at that memory address, we are going to use that as the target address of our jump. And we are going to start executing code from that location. Think of it as multiple levels of indirection. It's nothing more than that. You can keep creating these levels of indirection. Go to register, go to memory address, go to a different memory address, and all that. Let's look at one example. Okay, so you know how to convert for loops, if statements into assembly. Here, what we are doing is we have two arguments in this function. If x is greater than y, we return x minus y, otherwise we return y minus x. So you remember this template from 2300? Comparison, what is this doing? Where is it going? If or else. And then this is the if part. So this is the if block, and this is the else block, okay? So this is how, this is an old style transformation of C code into assembly. And if we tell the compiler, don't do any if conversion, it will spit out code like that. Now we will soon see what modern compilers do and what kind of support is there for doing this more efficiently. Once again, the template for converting a if else is you do the comparison. You do the comparison between x and y, and if the condition is not true, you go to the else block. Otherwise, you do the if block, and in both cases, you return to the calling function. Okay. And if we see what the compiler is doing, it looks like something. It's doing the test, and then if the test succeed or does not succeed, it goes to else, go to else. Here is the else block. Otherwise, it does the if block. Now, C does provide goto statements, but they are not used. Goto is considered a very bad programming practice. But this is just to show you what the compiler is doing. The compiler internally is using the goto style to transform the loop. So C provides a statement conditional expression. So this is a valid C statement. You do the comparison, you do the test, and you set the values in a single statement. So value equals, if the test succeeds, it will be set to x minus y, otherwise 1 minus x. So you don't have to write if else when you are setting the value of a variable depending on a condition. You can use an expression like that in C. Value equals test question mark x minus y, and then y minus x. And value will be x minus y or y minus x, depending on whether a test succeeds or no. So let's see how the compiler does the transformation. There is a special instruction called the conditional move instruction. Let me demonstrate that first, and then I'll come back to why the old style of using a branch instruction is a bad thing. Here, we have the same function. We are computing x minus, there are no branches here. There are no branches in this code. We are computing x minus y. We are computing y minus x. We are setting the condition codes with the compare instruction, and then we have a last instruction, conditional move, that will change whatever is stored in RAX if the test succeeds or no. Okay, so this here does x minus y. So here I'm moving RDI to RAX. RDI is x, so RAX is x, and then subtract RSI from RAX. So this is x minus y. This is y minus x. So RAX has x minus y at this point. So at this point, RAX contains x minus y. RDX contains y minus x. And remember that, recall that we need to put the return value in RAX. Okay? We need to put the return value in RAX. That's the convention. It contains, at this point, RAX. RAX contains x minus y. RDX contains y minus x. This is how we have set up our code. We do the comparison, and we do the conditional move. This is a conditional move. And this is the condition. This is from the table. This is saying less than. It's moving RDX to RAX. You see how if this move is not executed, if the condition is not true, then this transfer will not happen, right? And RAX will have what? X minus y. If after this comparison, this condition is true and this conditional move does take place, RAX will have RDX, y minus x. Okay, you can look at this code offline. So what's the difference between this and this over here? Okay, now it's giving me a different marker. There's a protocol. All right, so the two, this code over here is for the same function as this code over here. And after 1995, they introduced this instruction, conditional move. So why did they do that? Because branches are really harmful to performance. What we do today in our high-end processors, in our high-end CPUs, we don't execute one instruction at a time, one instruction every cycle. At any given point, we are trying to execute as many instructions as we can. Okay? And this phenomena is called instruction level parallelism. Now, branches are really harmful because whenever you encounter a branch, you cannot proceed until you know what? If the condition is met. If the condition is true or not, and what is the target address? If I give you a bunch of instructions without a branch, if there are no dependencies, you can go ahead and execute all those instructions in parallel. This is what the processors are trying to do. The moment you get a branch, you have to stop, because you cannot do anything. You don't know what the next instruction is going to be. This is why branches really kill performance. And they have something called a branch predictor to guess what the target address is going to be. Now, those branch predictors today have very high accuracy, and they can most of the time predict with a very high accuracy where to go next. But when they make a bad choice, when they make a wrong guess, the processor has to redo everything that it was doing for the last whatever. So branches really kill performance, and this kind of programming practice is really common. We do this all the time. Based on a condition, we set a value to one thing or the other, and we return that value. So that's why they put these conditional move instructions. Can someone guess? Think as broadly as you can. Can the compiler always do that? What is the problem here? What is the drawback? Okay, the drawback of branches is that they kill performance. When the branch predictor makes a wrong guess, the processor needs to redo a lot of things. But nothing is free. So what's the problem here? What? Takes a lot of memory space. Extra instructions. The memory space is due to what?
Due to they have to compute all the possible results of every branch.
All right, very good insight. In this code over here, you either execute the else block or you execute the if block, right? In this code over here, you are executing both instructions from both blocks. You are computing x minus y, and you're computing y minus x. Now, by the way, the compiler can do that, but the programmer did not say that. The programmer said, do one thing or the other. So the compiler and the processor, all of them together, the entire party is breaking the contract. There's a contract between the program and the entire tool chain and the processor. And we often break that contract. This is an example of how we break that contract. When you break contracts, bad things could happen. One bad thing is we are executing redundant instructions. We only need to execute one instruction, x minus y or y minus x. There is a bigger problem. What? Right. How can it be really, really harmful to do that? So imagine if you have code like, well, first of all, if these statements are really hard, if this is not one instruction, but many instructions, then probably it's better off going back to the old school transformation and let the branch predictor and those guys do the work. Because if this is 10 instructions, then you are executing 10 extra instructions. One problem. The second problem is you might dereference a pointer, and that might be an invalid address. There may be a memory protection violation, and the program will just crash. And so the programmer will be like, oh, but this wasn't supposed to happen. The else block was never supposed to execute. How did this happen? Well, this is where we have bugs in our real world applications. And that's why we want you to be aware of these transformations. These things happen in the real world. And the programmers are looking at their high level code and they're like, yeah, but this condition can never happen. Okay, let me look for the bug somewhere else. Well, they don't know what the CPU, what the compiler is doing. They need to know that. And the last thing is, I want you to think about this thing here, computations with side effects. Today, my setup, the whole setup is, I'm going to work a lot on this. Okay, I really want you to think about this. What is the problem here? The third drawback or the third bad case for doing this modern transformation of a conditional expression where you're setting a value of a variable depending on a condition. What is the problem here? It says x is greater than 0. That's a test. If the test is true, oh, you might not have seen that. Do you know this syntax? Do you know this? Is this have you used this in Java? What is it doing? What do we call this? After this statement, x star equals 7, will x change or no? Yay, that's a problem. So if the compiler goes ahead and says, okay, let me execute both statements, well, the programmer did not say that. The programmer said either multiply x by 7 and store it in x, or add x to 3 and store it in x. Because of compiler's transformation, you will first store in x multiplied by 7 and then x plus 3, okay, which is wrong. So compilers are really smart when they transform, or careful when they transform such statements into assembly. And a lot of compilers simply ignore conditional move because the heuristics to figure out when to do it, when to not do it are really, really difficult. And you don't want to do the wrong thing. Okay, loops are self-study. You study it on your own, because Charles has told me that he covers this in a lot of detail. Let's try to do one last thing before we call it a day. So the switch statement. Have you looked at a switch statement before? Right? It provides multi-way branching capability. You don't have to write a lot of if-else blocks. It improves code readability. We are not interested in introducing switch statements. We are interested in how they are translated into assembly. And more importantly, we want to learn about something that will be very useful later on, a jump table. A jump table. And what the jump table enables is the time taken to perform a switch is independent of the number of switch cases. You don't have to execute a lot of branches to go to the actual code that you want to execute corresponding to the switch statement. And a jump table is just an array where each entry is the address of a code segment corresponding to the switch. All right, so here's a jump state. It has some very interesting properties. First of all, a switch statement takes a variable inside parentheses, and depending on the value of that variable, the processor executes a specific code block. Okay, so here we have 5 and 6 that execute the same code block, right? Case 5 has no code in it. So we will just go to case 6 and execute from there. Now, if there was a break statement at 5, we will not do anything. But there is no break statement after case 5. What it is saying, whenever you see 5, go to 6. 5 and 6 are the same. So multiple case labels, you will notice that the cases, the are not, the range is not contiguous. There is no 4. So there is a missing case, and that is okay. And then there are fall through cases. So case 2 has no break statement. It goes to case 3. So what the programmer is saying, whenever you see case 2, execute w equals y divided by z, and w plus equals z. Okay. All right, so here's our jump table. So in memory, this is our RAM or memory. We have all the jump targets. So these are our addresses, the code addresses of the code blocks corresponding to each switch, each block in the switch statement. The jump table stores the addresses, the starting addresses of all the code blocks. Okay, now first of all, there's a default case. When none of the cases match, you go to the default case. So as usual, you do the comparison. You do the comparison of X, which is in RDI, with 6, because there are 6 cases. And if you are above that range, you jump to, there's an indirect jump to, okay, what is it doing? Okay, what is this trying to compute? This addressing mode here, this address mode here, what is in RDI? X, right? What is 8? Scaling factor. So in parentheses, what do I get? X multiplied by 8. Okay? And the dot L4 will add whatever dot L4 is to the resulting. Okay, looks like everyone is tired. Okay. So you get X, you multiply it by 8, and you add dot L4. So this is the read-only data portion. This is the RO data is the read-only data portion of your binary. L4 is the starting address of the jump table. And then we store the addresses of the code blocks corresponding to each switch case. Okay? So what is this trying to do? If this is our jump table in the previous code, so this here is saying jump to whatever is stored in memory location X multiplied by 8 plus L4. So X is our case index, right? 0, 1, 2. In fact, there is no 0. 1, 2, 3, 4, 5, 6. Why are we multiplying it by 8? Because each address is a 64-bit word. All right, we are looking at a 64-bit ISA, 64-bit architecture. Each of these dot L8 is 64 bits. Dot L3 is 64 bits. These are addresses. These labels are addresses. These are 64-bit addresses that we have stored in the jump table. And we want to jump to one of these addresses. corresponding to whatever x is. So we look at x, we compare it to RDI, sorry, we compare x to 6. If we are outside the range, we go to dot L8. Dot L8 is the default case. Otherwise, we jump to, it depends where we jump. It depends on the value of x. We scale x by 8 and add the start of the jump table in memory. Jump table starts at dot L4, the label dot L4. We take that address and we add x multiplied by 8. It's the same technique we use to index into an array using the scaling factor. So we fetch the target, we compute the effective address, we compute the address, and at this address is stored. What is stored at this address? The address of the code block that we want to execute. All right. So this is the indirection where indirection is really helpful. So at that address, we store the. Okay. Okay. So really impatient. Let me stop here. And we will have one more lecture on C to x86 before we move on to processes, virtual memory, and other things. Okay, thank you for attending the lecture, and
What about the advanced access?